This is my Physics 2211 Lab 1 motion of a falling object. So the purpose of this lab is to observe an object's movement as it's dropped slowly at rest. In this case, I dropped a folded piece of paper at a height of 1 meter. Some important information to know beforehand is the momentum principle. It states that the net force on a system is equivalent to change in momentum over change in time. From that, we get the equation net force is equal to delta P over delta T. And from that, we can derive the velocity update formula, which states the final velocity is equal to initial velocity plus the net force divided by mass times delta T. And also the position update formula, which states that the final position is equal to initial position plus the average velocity times T. Other things we need to know, the system will be the folded piece of paper. The surroundings will be everything else. We need to know the force of gravity, which is mass times the acceleration due to gravity, which is 9.8, and also drag force. And then the net force will be the force of gravity plus the drag force. So as you can see here, this is my setup for my lab. My the paper ball that I rolled up is like right there. You can't see it right now, but as I play, you can see all the data points as it fell. So from that tracker or video, I tracked all its points as it fell over every like 0.033 seconds. And as you can see here, it's a curved slope showing the effect of acceleration, like the gravity and net force on it. So my initial conditions for my code was I set the initial position to 0, 1, 0 because of the length of the fall. I set the mass of the ball to 0.005 kg because it's 5 grams. Um, the time I set to zero point 0.5 because the fall occurred over a duration of half a second, and then the system was the ball, surroundings, everything else. Yeah, also when simulating with no drag force, I set B equal to 0, and then as you can see down here, the net force would just be um, the mass of the ball times the gravity and the direction, which is j hat. Since it's just falling down, um, it would just be like 0, 1, 0 times the mass times gravity. And this is the effects that came out, the graph that came out with no drag. As you can see here, it would have gone further in half a second with than it did in my observed data. So this is my code including drag. This time, um, I initialized the coefficient of drag to 0.063. Everything else stayed the same for in the initialization part, but in the next part, when I in my while loop, I set in the net force, I had to set like the b times the magnitude of velocity squared minus the force of gravity because the drag force will always be in the opposite direction. And it's still j hat because it's only in the y direction. And as you can see here, this time the position time graph shows that it will finish always at 0. Like it will finish at 0. And it also shows in the velocity time graph another curve because it shows it like sloping and then inwards towards its terminal velocity where it will remain constant afterwards. So these were the points I graphed. Um, the one right here on the left is the observed data. On the in the middle is with the drag force, and then on the right is without drag force, the computed model. And as you can see here, the without drag force was much steeper curve, showing effects that drag force had, and then um, my drag force and observed data could have been different because of things um, like in my tracker how it would curve slightly, or maybe I measured the meter incorrectly, or other possible forces acting upon it. And then what does it mean? Which models predicted a terminal velocity? That would be the one with the drag force. We see this when the velocity starts tapering out, meaning it has reached maximum speed. And what if the object was initially thrown downward? Would the terminal velocity in this case be the same or different? It would still remain the same, but it just reached the terminal velocity faster. Thank, um, thank you.